Swayam Prabha. Digital India. Educated India.
Now, what are the raw materials that are required to make cement? The principal component of cement is lime. Okay. For lime, you need to get limestone. Okay. Limestone is needed to make cement. Any source that contains a large quantity of calcium carbonate is needed. Mostly it will be limestone because that contains the most purest form of calcium carbonate. Okay. Sometimes it may have impurities such as iron and alumina also. The other component is clay. So, the clay basically contains silica, alumina and iron oxide. Okay. So, limestone contributes calcium carbonate, the clay contributes silica and alumina, both of them have some little bit of iron oxide also. Okay. And then to this mixture, which is burnt and then converted to what we call as clinker, I will talk about that later, you also add another additive called gypsum. Of course, this is a material that you are all familiar with, right. Gypsum is added in the final stages of manufacture to control the rate at which cement will set once it reacts with water. Okay. So, you have these three principal raw materials for manufacture of cement. So, what are the production processes that are involved? First, of course, you need to select the correct raw materials. You need to break them down into very fine scale powder. After breaking them down into a powder, you mix them or blend them, okay, essentially mixing, right. You mix the raw materials together and then you burn them in a kiln, okay. We talked about brick kilns, right. Brick kilns were vertical kilns. So, you load the material at the bottom, you have the heat and then the gases go out of the top and then you take the material out which has been burnt. But in cement, it is not the same, you go with what is called rotary kiln. In cement, we produce with a rotary kiln. Okay, I will show you a picture of that later or a schematic of that later, that will make it much more clearer. So, you mix the raw materials together, you burn them together in a rotary kiln. That leads to the production of what we call as clinker. That produces what we call as clinker. This clinker comes out of the kiln and this clinker is then interground with gypsum to produce your Portland cement. Okay, so, gypsum is not put into the burning process. The material that comes out of the burning process, which is called clinker, is ground together with gypsum to produce Portland cement. So, this is basically a schematic that describes your Portland cement production process. So, you have your quarry from which limestone is getting extracted. After extraction, it goes through some crushing, right. You have primary crusher, secondary crusher and so on, right. Finally, you get fine ground limestone that is of the right size, okay. And that goes and gets stored in silos. You store it in silos. A silo is basically a vertical cylindrical structure, right. Okay. You might have seen silos for grain, silos for cement and other materials and so on. So, you store the fine ground limestone in silos. You also have storage silos which have clay and probably sometimes sand depending upon the silica content that you want. You do all the proportioning, right, and sometimes you grind the material together with the limestone and then send it to what we call as a preheater. If there is any free water, right, limestone is extracted from the quarry, right. In the quarry, the stone is not going to be exactly in the dry form, there will be some wetness in it, okay. So, without spending too much energy in actually trying to drive off this water, you may want to further send it to the preheater tower where any extra water that is there in the raw material will get removed, okay. And this water will get removed and then the materials will again blend together properly and then they are introduced into this chamber called the kiln. Now, that is called a rotary kiln because it is rotating at a certain speed, very slow speed of course. So, rotary kiln basically is rotating and what happens is the material that comes in here basically goes around the kiln by gravity. You do not need to force it in, it goes by gravity to the other end. And if you see carefully here, at the other end you have a flame. You have a flame which is burning at the other end. That means the temperature is very high here, So, high temperature in this end and a lower temperature in this end. So, as the material goes from one end of the kiln to another, it is subjected to a series of different temperature scales going as high as 1450 degrees Celsius. It goes all the way up to 1450 degrees Celsius. And as a result of this burning process, these raw materials, that is clay and limestone, get mixed together and also fused together to form certain compounds, which I will talk about later. That material comes out as clinker, and that clinker is cooled and then stored, okay, again stored in silos, and then finally it is proportioned along with gypsum and sent to the grinding mill, okay, where it is ground along with gypsum, interground along with gypsum, and then it is extracted as cement. And this cement is again stored in silos and then sent to job sites. To the job sites, typically cement is sent either in bags or in bulk. So, in a bulk, they are transported through these trucks which are called bulkers. Okay. So, depending upon the requirement of a job site, you may want to actually get cement in bulk or as bags. For residential construction, mostly you will get cement in bags, okay. But if you are supplying it to a centralized mixing plant for concrete, you will be sending a bulker which takes a large quantity of cement and discharges that into the material storage silo that is available at the centralized mixing plant. I will show you those things later, right. So, this is the overall process of cement manufacture. The most important part is the raw materials are ground to a very fine size so that they can mix and blend well. Then they are sent to a burning process in which they get fused together to form different sorts of compounds, and then the material comes out and it is cooled and then proportioned along with gypsum to produce the final Portland cement. So, what are the compounds or what are the oxides that are present in the cement itself? From the raw materials, that is limestone and clay, you get the following oxides: calcium oxide, silicon dioxide, aluminum oxide and iron oxide. If you think about cement in a nutshell, it is a mixture of these four primary oxides. In cement chemistry, calcium oxide is written as C, silicon dioxide is written as S, aluminum oxide is written as A, and iron oxide is written as F. Quite different from what you see in regular chemistry, right. C in regular chemistry would mean carbon, but here we are not talking about carbon, we are talking about calcium oxide as far as cement is concerned. There are also other oxides present depending upon the raw materials that you are using, like magnesium oxide, sulfur trioxide, sodium and potassium oxides. These are called alkali oxides. Sodium and potassium are called alkali oxides. Then you may also have other minor oxides which do not really have a bearing on how well the cement actually works. Now, you have all seen that cement appears grey in color. And why is that grey color? Obviously, it is because of iron oxide that is getting produced in the cement and the kind of atmosphere that you have inside. It is called reducing atmosphere, okay. Now, as I said, in the kiln burning, the raw materials are actually mixing up and then getting fused to form some compounds. So, you have these four primary compounds that are forming. What are these compounds? C3S is a mixture of calcium oxide and silicon dioxide. So, it is typically written as C3S to mean that it has got 3 parts of calcium oxide and 1 part of silicon dioxide. C2S is 2 CaO SiO2. C3A is 3 CaO Al2O3 and C4AF is 4 CaO Al2O3 Fe2O3. Very complicated because these compounds do not represent actual stoichiometric compositions of the materials that we see inside cement. Okay, in chemistry, when you think about compounds like calcium carbonate, it has got a very well defined stoichiometry. We do not write calcium carbonate as CaO.CO2, right? That is because it combines well to form calcium carbonate. Here, the exact composition of the material is not very well known, okay. The approximate compositions are what are represented here by these compound compositions C2S, C3S, C3A and C4AF. Gypsum, as you all know, is calcium sulfate dihydrate, 2H2O, right? And if you want to write gypsum in the language of cement chemists, you would be writing it as calcium sulfate dihydrate. So, in cement chemistry, gypsum will be written as C, S with a bar on top, or sometimes it is written as S with a dollar sign H2. Okay. Do not confuse yourself with this, do not worry about it, it is just the way that cement chemistry notation actually works. For the most part, you need to remember these 4 principal products that are present inside the clinker that comes out in the clinker. Of course, gypsum is added after the clinker comes out and proportioned together with the clinker to make your Portland cement. How much of these compounds are present inside the cement? Typically, when you think about modern cement, most of it is C3S. Nearly 50% or more than 50% is C3S. And there is a reason why this is so. I will come to that in just a minute. Okay. Apart from C3S, as I said, you have C2S, which is typically about half or less than half of C3S. Then you have C3A and C4AF, which are much smaller quantities. If you combine the C3S and C2S together, it will be nearly 80% of your cement. And of course, the remainder will be made out of your aluminates and gypsum. Okay. So, nearly 80% of your cement will be a mixture of C3S and C2S. So, primarily your cement is calcium silicate. Okay. We talked in the last chapter in stone, brick and mortar about hydraulic lime, right. Hydraulic lime is basically produced from impure limestone, burning of impure limestone. Again, that leads to the formation of calcium silicates. It forms smaller forms of calcium silicate. Here it forms larger forms of calcium silicate like C3S and C2S. Okay. So, what do these compounds basically impart to the cement? We will take a look at the reactions and the chemistry in just a few minutes. But what does the resultant cement have in terms of its basic physical properties? So, the specific gravity of the cement is 3.15. That means if you take each and every gram of cement and somehow you are able to calculate the mass and the volume of each grain, sorry, not gram. If you take each grain of cement and you somehow were able to calculate its approximate or exact mass and volume, what you will get by dividing mass by volume is the true specific gravity of the cement. Okay? That is the solid specific gravity of the cement. However, when you take it in bulk and put it in a container, what happens is the particles do not come very close to each other. There are voids or air gaps that you have inside. Okay? When you take a bulk measurement, you will actually see that the density is 1.5 to 1.6, not 3.15. Okay? Specific gravity is nearly half of that when you start putting it as a powder. This you would have seen in any of the any solid that you deal with. Even if you take sugar, right, measure the density separately, okay, but then put it in a container and then measure the density, you will find that the bulk density that you have in the container is smaller than the actual solid density of the sugar. Okay, and that is because it is not packing without any voids in it. Okay. Fineness of cement is expressed typically in terms of a surface area. So, if you take 1 gram or 1 kilogram of the cement and you were able to measure all the surfaces on top of the cement and represent that as a surface area, that is what is called a mass specific surface area. So, if you take 1 kilogram of cement, the mass specific surface area would be 300 to 350 square meters, okay, square meters, right. So, each and every grain of cement, if you take, the fineness would be in the range of 300 to 350 square meters per kilogram. So, what happens when you mix the cement with water? You might have seen what happens when you mix lime with water. Okay, it rapidly reacts with water and converts to calcium hydroxide. Now, cement on the other hand has a controlled reaction with water. Nevertheless, the reaction of cement with water is also exothermic. It releases heat. Okay? Heat is released when cement reacts with water, and this heat released is called the heat of hydration. So, the entire process of reaction of cement with water is called hydration. Okay? Now, what happens in this hydration is that you have these cementitious compounds, that is C3S, C2S, C3A and C4AF, and along with calcium sulfate that's coming from gypsum, they interact together and produce a certain set of compounds. We'll talk about those in just a minute. Now, if your reaction is faster, you evolve more heat rapidly. Now, you can look at it in two ways. One is your heat is getting evolved rapidly caused by a very fast reaction. That means your setting and strength gain of the cement will be much faster. But at the same time, you also have to remember, if you are releasing a lot of heat very fast, then your potential for cracking is also more. So, have to be very careful about how you control the rate of reaction of the cement. And the heat that is developed obviously depends on the heat of hydration of individual compounds. Each compound reacts at a different rate. Okay? It turns out that the compound which we call as C3A is the fastest reacting compound. Okay? It is responsible for setting an early strength, and it possesses a high heat of hydration. Okay? In fact, in cement, if you do not mix gypsum, if there is no gypsum, your C3A reacts rapidly with water with a lot of heat evolution and leads to what we call as flash set. So, in other words, the cement which reacts with water without any gypsum, the cement without any gypsum, when it reacts with water, you will lead to a condition which is called as flash set. That means it will suddenly harden and it will not be recoverable beyond that. That is why we want to add gypsum to take care of C3A, otherwise the C3A will go crazy. Okay? Without gypsum it will go crazy. So, you want this gypsum to be there to regulate the rate at which C3A reacts. But nevertheless, the interaction between gypsum and C3A is still giving rise to some early strengthening and setting of the cement. Okay? But as I said, your cement is mostly C3S because it is containing more than 50% of C3S. So, C3S also is responsible for early strength gain. That is why we want more of it, so that we can gain strength early. Right? Most modern construction projects, we want to finish fast and get over and go to the next stage. Right? So, for the concrete to be able to gain strength fast, the cement should be also rapidly strength gaining. Okay? So, here the compound that is primarily responsible for the high early strength of the cement is C3S. Okay? So, if you want early strength gain in cement, you want a cement with a high C3S content. And of course, it does not come without any price. You have to pay a price for it. It possesses a high heat of hydration. That means it evolves heat rapidly and the potential for cracking could be significant. On the other hand, when you have a cement which is rich in C2S, dicalcium silicate, it is very slowly reacting and it has a low heat of hydration. So, it will possibly not even react in the first few days of cement coming in contact with water. So, your C2S reaction may actually start very late and it is actually responsible for the long term strength of your concrete. Okay? So, it will slowly be reacting. As long as that is water available, it will continue to react and then provide strength over the long term. As I said earlier, higher heat evolution means faster reaction. Finer the cement, the faster the reaction. If you can grind the cement to a very fine size, you can increase the rate of reaction. Of course, same thing, you take sugar and crush it into a smaller size, it dissolves much more rapidly in water. Same thing in cement, when you crush it to a smaller size, it reacts more rapidly with water. And it will also liberate a lot more heat. Right? So, you need to take it very carefully to produce the cement which has the right level of control over its setting and its strength gain properties, because all this needs to satisfy the needs for a particular application. Just to give you an example, if you are going to construct a building, the columns of the building are going to be rapidly taking very high levels of load. So, in such cases, you will obviously want to go with a cement that gains strength rapidly. In the case of a dam, on the other hand, you have massive concrete, very large blocks of concrete. So, what is going to happen in that case? The heat that is getting liberated by the cement hydration is going to be so large that you may get thermal stresses in the dam. okay, because the concrete section is massive. The heat that is getting generated inside does not dissipate out quite easily. So you get build-up of thermal stresses, and that is not good for the concrete because it will lead to cracking. Okay. So because of that, in such cases, we would like to use a cement that produces less heat, right? So in those cases, we may want to go for cement that is rich in C2S or adopt alternative strategies, as I'll talk about later. Now, what does the reaction of cement with water produce? The calcium silicates obviously have to produce some calcium silicates. The calcium aluminates have to produce some calcium aluminates. So let's see what it produces. The calcium silicates basically end up in producing calcium silicate hydrate, CSH, and calcium hydroxide. They produce solid components called calcium silicate hydrate and calcium hydroxide. Both these solid components fill up the volume that was previously occupied by water. So if I show you a picture of cement particles in water at time t equal to 0, right? The cement particles have come in contact with water, and slowly what's going to happen? The reaction products are going to start forming on the surface of the cement particles, right? And then occupy the space which was previously occupied by water. So in other words, with reaction, as reaction proceeds, the space previously occupied by water gets filled by the products. What does this mean? This means that the porosity, because space filled with water is basically empty space where there is no solid, so its porosity reduces as your hydration continues to happen. So any of the solid compounds that reduce the porosity will ultimately lead to an increase in your strength. Okay? So calcium silicate hydrate and calcium hydroxide both cause an increase in your strength because they are contributing to a reduction in the porosity. But the major component is still your CSH, and it's the primary strength giving component. Calcium hydroxide can be chemically altered quite easily. For example, if there is external carbon dioxide, you've seen it in the case of lime water, what happens? Carbon dioxide reacts with calcium hydroxide to form calcium carbonate. So in this case also, in cement also, there is free lime that is generated from this reaction, not free lime, hydrated lime that is generated from the reaction, and this hydrated lime can be quite easily reacted with a chemical species that is coming into the concrete from outside, like chloride or a sulfate or a carbonate, for instance. Okay? So it is susceptible to chemical attack, but that doesn't mean it's a bad product. It is a good product because it is filling up pore spaces inside the concrete. And the calcium hydroxide also regulates pH of the cement paste. General cement paste will have a pH of around 13 or more. That means it's highly alkaline. And interestingly, what happens is at this pH, steel is free from corrosion. When the concrete produces a very highly alkaline environment, it protects steel from corrosion. When you have conditions that reduce this alkalinity, you will lead to corrosion of steel. So you want this highly alkaline environment, which is getting regulated by calcium hydroxide, to be present in your system. Okay? What about the calcium aluminates? They go into reaction with the sulfate, as I said, because sulfate controls the rate of reactivity of aluminate and forms what is called calcium sulfoaluminates. These cause initial strengthening and stiffening of the concrete. Okay? So long-term strength gain is all because of CSH, calcium silicate hydrate. The initial strength could be because of CSH, could be because of aluminates, and so on and so forth. Please remember, any solid product is going to occupy porosity or occupy the water-filled space and reduce the porosity. So as porosity reduces, the strength goes up. As porosity reduces, the strength goes up. Okay, so now you understood now what the chemistry of cement is, how do the compounds of cement actually react. What happens when cement comes to a job site? How does the contractor or the person who is actually doing the application of the concrete, how is the quality of this material ascertained? You need to do some basic laboratory investigations to understand the quality of the material that has been received on site. So for that, of course, the Indian standards gives you the guidelines as to the tests that you need to do. Okay. The important tests that are required for cement analysis are the test of consistency and setting time, which is done with the help of a VICAT apparatus. Many of you will have this test in your laboratory classes in your further semesters. Okay. So you have to determine what is called initial setting time and final setting time. What do you think is the importance of initial and final setting time? Now, you know that when the concrete is first prepared by mixing water into it, okay, cement and water come into contact, the concrete is still very fluid. Okay. You have some time with which this concrete can be taken and put into the formwork and then consolidated and finished on the top surface. So there is some degree of or some amount of time that you get to actually complete all the operations. Okay. After you place it in position, it slowly starts stiffening and gaining strength. Okay. Beyond that point, you will not be able to rework the concrete. Okay. So initial set basically is the point at which your concrete just starts to set. That means the reactions just gain in speed. And final setting is the point where the concrete has gained its shape or form and it's not going to change the shape or form beyond that. Okay. So initial set is the time available for you to work with the concrete. Beyond that, you will not be able to mold the concrete in any way you want. Final set is the point beyond which the concrete has a definite shape. Now, it does not mean that at final set your concrete has strength. No, concrete continues to develop strength beyond that. Okay, we will talk about that later, that as long as water is available, concrete will continue to develop strength. Okay. The other important characteristic that you want to test on your cement is the soundness. Now, sometimes because of the nature of the raw materials and the nature of the process which manufactures the cement, you may have free calcium oxide or magnesium oxide that is present inside your cement. What will happen is, when this reacts with water, it can lead to the formation of calcium hydroxide or magnesium hydroxide, and that may lead to increase in volume. So, in a set cement paste, if you have too much excess of this free lime or free magnesia, the increase in volume will lead to cracking. That is what is called unsoundness. So, that needs to be properly checked. It is called unsoundness. Okay. So, soundness is the ability to retain the volume. Unsoundness means that after setting the volume is increased. So, you do not want that volume increase to be uncontrolled, otherwise your concrete cement will not be usable. Okay. Then you have to measure also the strength of the cement. Okay, in real life design, when engineers are working on site with concrete, they will only be worried about the strength of the concrete. That means the strength that they get from the composite material, that is inclusive of water, cement, sand and stone. But to ensure that the cement is of right quality and will produce the desired effect in concrete, we also have to test all these characteristics, and finally we also need to test the compressive strength of the concrete. Now, interestingly, the compressive strength of the cement is not measured on just a mixture of cement and water, it is measured on mortar. That means it has got some part of water, cement and the sand. Why do we want to use mortar to determine the strength of the cement? It is something that you should think about. The whole point of the matter is, cement does not function as a strength giving component on its own. It basically provides strength by binding the aggregate particles together in a concrete. That is why we want to test the strength of the cement with respect to its nature of binding. Okay? So, we want to test the binding strength of the cement, and that is why we do that test on mortar. So, please remember, we want to test the strength of the cement to define its binding characteristics, how well it binds together the aggregates and keeps them in place and provides stability and resistance to loading. And that is basically the strength that we are trying to determine from the compressive strength test. That is why we do it on mortar and not on cement paste. Okay. Now, the other reason why we want to do it like that is because if you just mix cement and water, it will start shrinking once the structure hardens. There will be shrinkage. Presence of sand reduces the extent of shrinkage that happens. We will talk about shrinkage separately when we talk about concrete, but essentially to keep the volume dimensionally stable, it is important that you do the strength test on mortar and not on cement paste. Now, one thing I forgot to describe is what is consistency. Consistency is defined typically as a minimum water content that is required to produce a paste which has a certain characteristic. That means a certain workability, a certain consistency. Okay. All these will become a lot clearer when we talk about the properties of concrete. Okay. But anyway, please remember, you need to test the cement that is arrived at a job site for its consistency, its initial and final setting time, soundness, and finally compressive strength. All these characteristics have to be met before the cement can be pronounced to be good enough to be used in concrete. And of course, you need to compare it with the standards. So, you have to compare the cement quality that you measure on site with what is prescribed in the standards.